start with the question. We denote the inlet gas flow rate as Qi and the pressure inlet as Pi, and the flow rate outlet as Q0 and pressure outlet as P0. So first we make the assumption, and the first assumption is the molecular weight, volume, temperature are constant, and the second assumptions made are gases obey ideal gas law. First, let us start with the mass balance. The accumulation of mass equals to mass inlet minus mass outlet. The d rho v over dt is the accumulation of mass, and the rho I qi is the mass inlet, and rho naught q0 is the mass outlet. As we assume the gas obey ideal gas law, so rho equal to Pm over RT. The m is referred to the molecular weight of the component. So then we substitute the rho into the equation. And as the molecular weight, volume, and temperature are constant, we can take it out to simplify the equation. In order to further simplify the equation, we divide both sides by mv over RT. And this is the dynamic model we get. So for steady state, the difference in pressure according to time is equal to 0 in steady state. And so for the pressure and the volumetric flow rate are also in steady state. And this is the steady state model that we get.
According to the problem, it is given that it is a constant whole-up CSTR with a constant volume 46 meter cube. Inlet flow rate is 2.4 meter cube per minute, and the concentration inlet is 8.01 kilomole per meter cube, and the temperature have to be maintained at 350 Kelvin. The assumption we made is, since it is a CSTR, it will have perfect mixing. That means like the component inside the tank will be equal to the component outlet. The volume is constant, density is constant, and since K is given in the unit of 1 by minute, we assume that it's a first order reaction. Now we start writing the mass balance. d rho v by dt is equal to rho inlet flow rate minus rho outlet flow rate. Since rho is constant, it can be taken out and it can be cancelled out from both sides. Since it is a constant volume, there will be no change in volume, thus dv by dt will become 0, equal to qi minus q0. After rearranging and stuff, qi will be equal to q0 will be equal to q, which is also equal to steady state q bar. Now we continue writing component balance. dCA naught V by dt is equal to Qi CAI minus Q naught CA naught minus rate into volume. According to the chain rule, dCA naught by dt will be equal to CA naught dV by dt plus V dCA naught by dt. But since the volume is constant, dV by dt will become 0. and thus dCA naught V by dt will be equal to V dCA naught by dt. After that, we put the value back into here, and thus dCA naught V by dt will be equal to V dCA naught by dt. Q is constant, so Qi and Q naught is equal, so Q will be taken out. CAI minus CA naught minus RV. Then we divide both sides by volume, so dCA naught by dt is equal to Q by V. CAI minus CA naught minus R. R is equal to KCA naught, where K is equal to K naught e power of negative E by RT, and thus R will be equal to K naught e power of negative E by RT into CA naught. Then we put the R value back into here, so dCA naught by dt will be equal to Q by V. CAI minus CA naught minus K naught e power of negative E by RT into CA naught. From that term, we can find out that the nonlinear term is equal to e power of negative E by RT into CA naught. From here, the nonlinear variable have two variables, one is temperature and one is concentration. So the linearization formula will be for two variable one. F of T of CA naught will be equal to F of T bar CA naught bar at steady state plus differentiate in terms of temperature first, and then differentiate in terms of concentration. So after putting the value back in, F of T bar CA naught bar will be equal to e power of negative E by RT bar CA naught bar plus, we will differentiate in terms of temperature, and then we'll differentiate in terms of concentration. After solving all, this is the final equation we got, which is equal to e power of negative E by RT bar CA naught bar plus CA naught bar e power of negative E by RT bar into E by RT bar square T minus T bar plus e power of negative E by RT bar CA naught minus CA naught bar. Now we put the linearized term into the equation. dCA by dt is equal to Q bar by V bar CAI bar minus CA naught bar minus K naught. This whole term was K naught e power of negative E by RT CA naught, which was before linearization. Now after linearization, we put the whole term back into here, and we'll leave it as equation 1. Now we write the steady state equation. dCA bar by dt is equal to Q bar by V bar CAI bar minus CA naught bar minus K naught e power of negative E by RT bar CA naught bar. Since it is steady state, dCA bar by dt will be equal to 0, and the given value will be inserted here. After that, we solve to get the CA naught bar, which is equal to 0.32056 kilomole per meter cube. Now we minus steady state equation, which is equation number 2, from the linearized equation, which is equation number 1. So the formula we will get is dCA naught minus dCA naught bar by dt will be equal to Q bar by V bar CAI minus CAI bar minus CA naught minus CA naught bar minus K naught e power of negative E by RT E by RT bar square CA naught bar T minus T bar minus K naught e power of negative E by RT CA naught minus CA naught bar. Now we will write it in terms of deviation form. That means we will minimize CAI prime, which will be equal to CAI minus CAI prime bar. CA naught prime is equal to CA naught minus CA naught bar. T prime will be equal to T minus T bar. Like we minimize it, so we got the equation in deviation form, which is CA naught bar by dt is equal to Q bar by V bar CI prime minus CA naught minus K naught e power of negative E by RT bar into E by RT bar square CA naught bar into T prime minus K naught e power of negative E by RT CA naught prime. Finally, we just put the value in which is given 2.4, 4.6 Q by V and everything else, and also CA naught bar, which we already calculated before. After putting all the values in, we finally got the dCA prime by dt will be equal to 0.0522 CAI prime minus 1 minus 3037 CA prime minus 0.0132 T prime.
A processed liquid is continuously fed into the perfectly mixed tank, and the feed rate is at 25,000 kg per hour, and it has constant density of 800 kg per meter cube and constant heat capacity of 0.5 kcal per kg degree Celsius. The hold up in the tank is constant at 2080 kg of the liquid. The inlet feed temperature is 30 degrees Celsius. The saturated steam is at 150 degrees Celsius to heat up the processed liquid. At the initial steady state, the tank temperature is 90 degrees. Derive a mathematical model of the system. First, we have to list the assumptions. The first assumption is the liquid has constant density, the liquid has constant heat capacity, constant volume, and perfect mixing. So first, mass balance. d rho v over dt equals to the mass flow rate in minus the mass flow rate out. Since we know that the density and the volume are constant, so this term becomes 0, and hence the inlet flow rate, mass flow rate equals to the outlet flow rate, and also we standardize it with W. So next is the total energy balance. du over dt equals to mass flow rate in multiplied by the enthalpy in and minus the outlet mass flow rate and outlet enthalpy plus the heat supplied into the system. For liquid system, delta U over delta T is equivalent to delta H over dt. Therefore, du becomes d rho v Cp bracket T minus T reference over dt. And the W is the common factor, Cp T inlet minus T reference and minus Cp T minus T reference, and lastly plus the heat supplied into the system. For constant density, volume, and heat capacity, we can bring up the constant value out from the derivatives, and also we factorize it, and the T reference in the end is cancelled off, so we have WCP T1 minus T plus Q. We move the constant to the right hand side, so we get the derivatives T dt over dt equals to W over rho v T1 minus T plus Q over rho v Cp. So this is the dynamic model of the system. At steady state, there is no change in temperature. Will be 0 equals to the mass flow rate at steady state divided by the rho v, and inlet temperature at steady state minus outlet temperature at steady state plus heat supplied at steady state divided by rho v Cp.